So what I would like to discuss in this video is the relation between Cartesian coordinates and spherical coordinates. In particular, of course, what this means for formulating the Schrödinger equation in 3D and these two different coordinate systems. So the center of interest will then be the definition of the Nabla and corresponding Laplace operator in both coordinate systems. So this here is our 3D coordinate system in Cartesian coordinates x, y, and z, and we'll now consider a vector r in these three coordinates. So it's described in terms of x, y, and z coordinates. And so the relation to spherical coordinates is given as follows. So in spherical coordinates we would express this in terms of three coordinates, which are an angle theta, so it's the so-called polar angle, the length of this vector, which is just called r. This is the absolute value of this vector r. And then we have another angle, the azimuthal angle, and this is defined as follows. So first of all, I basically project this vector into the xy plane, and then I have a projection on the x-axis and I have a projection on the y-axis. Okay, so and the angle that we have with respect to the xy plane here, that is called the angle phi, the azimuthal angle, and this defines our three coordinates. Now the relation between x, y, and z and these new coordinates is given as follows. So the x coordinate, that is the coordinate here, okay? So this value of x along the x-axis is given as r times the sine of theta times the cosine of phi. So how can we see this? So the length on this green line here along this angle phi, so to speak, corresponds to the projection of this angle of this vector r into the xy plane. Okay, so this is given by sine theta. So how can I see this? If I just make a sketch here of the z-axis and this green line here from here, okay, so then I have my blue vector somewhere here, and this is our angle theta. Okay, so what I'll now do, I'll just basically drop a line down to the to this green axis, and so this length on this green line here corresponds exactly to sine theta. Okay, so this length is r times sine theta. Okay, so this explains this first part of this expression here. And now I still have to project this on the x-axis, and this now just corresponds to the projection of this point here down on the x-axis. Okay, so I can yet again draw such a diagram. So now I have the x-axis, and I have this green line here. Okay, and this angle here is phi. So I'm just basically redrawing this triangle here in the xy plane, and now I have this point here somewhere, which is exactly the projection on the green line which we had from here. And now I just project this once again onto the x-axis. Okay, like this, and this is exactly the cosine. Okay, so I can remove these plots, and with exactly the same argument we can then write down this y is the sine theta times the sine phi. So the first projection is as before, the length is projected on this green line here, but now I project against the y axis, and therefore I have a sine phi here, and the last one is r times the cosine of theta. Oops. Theta. So another way of writing this is I can say that I have unit vectors into the z, so Ez hat, I call these hatted unit vectors. This is the y unit vector, and then I have a unit vector in the x direction. And with these unit vectors I can rewrite the vector r as r times sine theta cos phi times ex plus r times sine theta sine phi ey plus r times cosine theta ez. So now we have a mapping between the coordinates, so the Cartesian coordinates and the spherical coordinates x, y, z and r, theta and phi respectively. Now the physics problem we want to attack are the ones where we have a radially symmetric potential, which means the potential will not change if you just change the angle or the position with respect to the center of the potential on a sphere of constant radius. So basically you can imagine that, well, you have the surface of this three-dimensional sphere here, and as long as this radius moves on the sphere, nothing happens. Which means that the potential, the value of the potential does not change. In all the previous problems we have considered in this course, we had to evaluate the Schrödinger equation, in particular the time-independent Schrödinger equation, in terms of kinetic terms. So these were derivatives with respect to the coordinates and the potential, which differed from case to case. Now here we're going to consider these radially symmetric potentials, and we therefore also, in order to take advantage of the nice properties of these spherical coordinates, we need to basically find an expression of the kinetic terms in terms of these spherical coordinates. So in short, this means we need to find an expression for the square of the gradient or Nabla operator, the Laplacian, in terms of the spherical coordinates. So the first step into this direction that we'll make is to find an expression for the unit vectors in these new coordinates. So we had these unit vectors ex, ey, and the z hat. So the hat is just that it's normalized to 1. And we're now going to try to find the corresponding expression for the direction of r and theta and phi. So the way we can do this is to say we have a vector in the r direction. So we leave the normalization until later. And we say it's defined as dr vector over dr. So what does this mean? Basically, we say we have a vector r, this is blue vector, and in order to find the coordinate system in the r direction, so the axis in the r direction, we wiggle around this vector r with respect to r, which is the radial direction. So what does this mean? We can write this out because we have an expression for r vector in terms of the new coordinates, and I can immediately take the derivative with respect to r. So what this means, I have to take the derivative of this whole expression with respect to r. So then I get a sine theta cosine phi times ex plus sine theta sine phi ey plus cosine theta ez. So this is our candidate for a unit vector once we've normalized it into the r direction. Good. So we can do the same with the other directions. So the direction theta will be, we wiggle r with respect to theta. So what I mean with this, I have again my vector r, and I now basically wiggle around in this plane at constant radius in the direction of this angle theta. Okay, so I make theta a tiny bit larger, tiny bit smaller, and that corresponds to the derivative. Okay, so that gives me, I have to now take the derivative of this expression with respect to theta. So this gives me r times cosine theta cosine phi ex plus r times cosine theta sine phi ey and minus r sine theta e hat z. Good, and last but not least, we do the same in the phi direction, so dr d phi equals, we get minus r sine theta sine phi ex hat plus r times sine theta cosine phi ey hat, and there is no term depending on the angle phi in the z direction, so there is no contribution from there. Now, I said we're going to leave the normalization till the end, and I'm just going to give it to you. So the normalized or the unit vectors are in the r direction just er, so you can check yourself that if you check the norm of this or the magnitude of this, it will be 1. Then in the theta direction, we need a 1 over r to make this normalized. And in the phi direction, we get a 1 over r sinus theta e phi. Okay, here we are. We now have the unit vectors in the r, theta, and phi direction. So let's see whether we can find an interpretation of this. So in fact, what happens is that instead of having our coordinate system in the Cartesian coordinate along the x, y, and z axis, we now have a new coordinate system which sits at the tip of this radius vector. Okay, so if I try to draw this, now we have a unit vector which is along the direction of the radius. This is e hat r. Then we have already seen we have a unit vector in the theta direction. Okay, this is our e theta hat. And then if we wiggle around with phi, you can imagine that at constant radius, the wiggling of phi will basically translate this whole thing around a huge circle around the z-axis. I'm not very good at drawing this. So basically, the phi vector will be the tangent to this circle. So it will be in this direction. Okay, so this is e hat phi. Good. And you can check that these vectors are indeed orthogonal to each other. So in fact, since they are normalized, they are orthonormal. Good. So for the following, we'll just introduce an observation. So if you build this scalar product of some vector A with a unit vector, so let's say B hat, so that means that B is a vector, but it's of unit length, then this is the same as the absolute value of a vector times the cosine of the angle theta. And the angle theta is as follows. So we have B here, and you have a vector A here in this direction. So, and this is the angle cosine. So basically what this gives you is, this is the length of this is the absolute value of A. And so basically it projects onto the axis here. So what this means, if you have a vector A and multiply it with this unit vector B, it gives you the component of this vector A into the B direction. Okay? So the reason why I'm saying this is, what we'll now try to do is to find out what the gradient in spherical coordinates looks like. And what we're going to do is we're just going to take the gradient as we know it, the one in Cartesian coordinate, and project it on our new coordinates. So you could imagine that in this vector A would be our gradient, and this vector B would be one of our new coordinates. Okay, and then we get the projection of the Cartesian gradient onto our new coordinates. So in particular, I start off with E hat R times our gradient vector. So remember that the gradient vector is d over dx, d over dy, d over dz. And if I write this down, I get that this is dr over dr times the gradient vector. And I can write this out in components. So this is a scalar product. So the first component of this r, dr, with the first component of this nabla gives me dx over dr times d over dx. So the first part is just the first component of this dr over r, and the second part here is just the first component of the Nabla operator. And then I go on, so I get dy over dr, d over dy, plus dz over dr, d over dz. And then I realized that this is nothing else than kind of a chain rule. So these dx, dx, dy, dy, dz, dz, they cancel. And what I end up with is, let me just wipe this bit here out. So what I end up with is that this is d over dr, and this is the gradient in the r direction. So it's the first component of our new gradient operator, or Nabla operator. And then correspondingly I get E hat theta times Nabla, and that is then, I have this normalization 1 over r, dr over dr times Nabla, and then I get 1 over r, dx over dr, d over dx, plus dx over, dy over dr, d over dy, plus dz over dr, d over dz, and that is nothing else than 1 over r, d over d theta. So this is the second component. And then we have the last component. If we take the scalar product between the unit vector in the phi direction and Nabla, so we project the gradient operator onto the phi direction. This is 1 over r sine theta, dr Nabla. So I don't have to do this in detail because it's exactly the same procedure. Get 1 over sine theta, d over d phi. So with all this, I can rewrite my new Nabla operator in spherical coordinates as Nabla being E hat r, the derivative d over dr, plus E hat theta, 1 over r, d over d theta, plus E phi hat, 1 over r sine theta, d over d phi. So it seems at first that we are almost there. We can just write d, so the Laplace operator, which is the square of the Nabla, by multiplying out this dot product of theta with itself. Now the slight issue here is that if we go back to the top, to our sketch here, while for Cartesian coordinates the unit vectors were basically always in the same direction, x, y, and z axis do not change, it turns out that this coordinate system in spherical coordinates depends on where you are. Now if you had an r vector which would point, say, over here, it's conceivable that this local coordinate system would really change because we are at a different point on the sphere, and in fact the e theta and the phi, they span the tangent space of the sphere. So in contrast to the Cartesian coordinates, where the unit vectors are constant, you don't depend on your vector r, the spherical coordinates depend on your position. So basically the unit vectors are dependent on your particular point in space. When I now build the dot product of Nabla with itself, and this goes as follows. So if I have Nabla dot Nabla, I will get an er d over dr plus e theta hat times 1 over r over d over d theta plus e phi hat 1 over r sine theta d over d phi, and this will act on this exactly same object. Okay, so you see that, for instance, this differential operator here, when we multiply this whole two brackets out, will act on all of these individual terms. So it will act, and the product will on er hat on d over dr, and then this dr will also act on e theta hat on 1 over r, and so on all these individual terms. So in order to see how dr acts on er, we can remind ourselves of the expressions for E, R, E theta, and E phi in terms of the individual angles. Okay, so if we do this, we can write down the expressions for the individual derivatives as follows. So we get d over dr of E r hat equals 0. We get d over dr E theta hat equals 0. And we get d over dr E phi hat equals 0. Now this is clear because if we go up again, none of these unit vectors depends on r because we have normalized them. Okay, in each case the r dependence cancelled out. Okay, so then let's continue. We can build d over d theta of er hat, and that gives us theta. Gives us e theta hat. So how does this go? If we take er and take the derivative with respect to theta, we get cosine theta, and a minus sine theta. And then you see that this is exactly the the unit vector in the theta direction. Okay, so hence we get this result down here. And now the same happens for the others. I'll be quick here. So this will be d over d theta of E theta unit gives us minus the unit vector in the r direction. And then we have d over d theta of E phi hat, and that is 0. Okay, good. So we get d over d phi, E r hat, and that gives us a sine theta E phi hat. And then we have d over d phi E theta hat giving us the cosine theta times E phi hat. And then last but not least, d over d phi of E phi hat gives us minus sine theta er hat minus cosine theta E theta hat. Okay, so this is our observation here, which we'll now use to write down the full square dot product, so of the Nabla, the Laplacian. And to make it a bit easier, I'll let it act on some function u. So then let me just multiply out all this and acting on a function u. So from the first term here, acting on the bracket on the right hand side, I don't get any contribution from r acting on the unit vectors because we've seen here that all these derivatives are 0. Note also that scalar products like er times E phi, for instance, are 0 because the unit vectors are orthogonal. Okay, so there are no further terms from the first term here acting on the second bracket. And then we can go on. So let me just write down from the first bracket, then we only get over d squared over dr squared acting on u. Now from the second bracket, we get two contributions. Namely, the first one is this d over d theta acting on the unit vector er. We've seen that d over d theta acting on a unit vector er gives us a unit vector e theta, which then multiplies with this term. And then there's another term when d theta simply acts on d theta, because e theta hat with e theta hat just gives a 1. So the two terms I'm getting here are plus 1 over r d over dr acting on u plus 1 over r squared d squared over d theta squared, also acting on u. Okay, and then I'll just give you the last couple of terms. This is when this term is multiplied out with this bracket here. So the contributions are plus sine theta over r sine theta d over dr u plus 1 over r squared cosine theta over sine theta d over d theta u plus 1 over r squared sine squared theta d squared over d phi squared, also acting on u. Now the final step, I'll just give this to you, is we can write this more compactly as 1 over r d squared ru over dr squared plus 1 over r squared sine theta d over d theta sine theta du over d theta, and then plus 1 over r squared sine squared theta d squared u over d phi squared. And the simplification you can easily check if you take the derivatives of this function. You will recover the terms where you have the derivatives with respect to r in the first line and correspondingly with the other terms. That's it. So this is the Laplace operator in spherical coordinates derived from Cartesian coordinates.